Hi everyone, welcome back. In this section, we're going to look at functions of several variables. This is the first section in chapter 14, and chapter 14 is all about functions of multiple variables and the calculus of such functions. So for example, we will be looking at how to represent these functions as surfaces, how to visualize them as surfaces, how to look at things like tangent planes, do derivatives, solve optimization problems. So basically everything we did in calculus 1 for functions of a single variable, we'll look to extend that for functions of multiple variables. So what is a function of multiple variables? How could these things perhaps come up in practice? That's our first motivating problem. So we're going to find the maximum possible product, or at least the problem is. We're not going to find it in this lecture. We're going to pose the problem here, see what kind of ingredients are needed in order to solve such a problem, and then defer the actual solution to a later section when we have the necessary tools to solve it. But for right now, we're just look at the setup of this problem. What is it saying? We're going to find the maximum possible product of three positive numbers whose sum is 120. So we want to find x, y, and z. So find numbers x, y, and z such that x plus y plus z is 120. And what do we want? We want the product to be maximum. So and I'll leave a space and I'll write x, y, z. So leave a space in front of x, y, z. We want this to be maximum. Maybe I'll say to be maximum. So we want this to be a maximum. So we want to find three numbers whose sum is 120 and whose product is a maximum. Now what we can do is we can define a function to be exactly that product. So it takes three numbers in, x, y, and z go in, and what it sends out is the product, x times y times z. So what we're interested in here is trying to find the maximum value of this function, which I've called capital P. P for product, makes it easy to remember. I want to find the maximum value of capital P when the inputs come from this set of values that satisfy x plus y plus z equals 120. So we now imagine this as an optimization of a function problem. We want to optimize the function P, find the maximum value of it when we restrict the inputs to be in this domain where x plus y plus z is 120. The thing we've just introduced here is this notion of a function of more than one variable. Here it's three variables, three inputs, and the one output is the product. That's the topic of today's lecture. It's these kinds of functions, functions of multiple inputs, or what we call functions of several variables. So as a definition, let's talk about first a function of two variables. So a function of two variables defined on a domain D in the plane is a rule f that associates with each point in the domain a unique real number output. So it's a rule which we've given a name to. It's f here, but the rule or the name I gave above for the function of three variables was p above. The name doesn't really matter. It's just whatever name you decide to use. We've got an input. And then once that input goes into the function, we get an output. And the output is denoted by the rule name situated on the left of what went into it. So we read this as f of x comma y. A function of three variables just has three inputs going into it. And so it would be denoted by this, f of x, y, z, where x, y, z comes from the domain, the possible values in space that we're allowed to plug into our function. Now, the way we typically view functions is through their graphs. This is how we can visualize them. And so I'll just give you an example of how we would visualize this definition. So I will do the case where we've got a function of two variables, f of x, y. Two variables go in, a value comes out. The value that comes out will assign to the variable z. So that'll be along this z-axis. Our domain for this function f is some collection of points in the plane. So there's our domain, some set down here, which is D. If we pick a point, let's say x comma y down here in the plane, actually I don't really need to label it. We pick a point and I plug it into my function f, then what happens is I get a triple. I get two inputs, x, y, and then this output, z, and that produces a point in space. That point in space is a point that lives on the function. So this would be a point where, now I'll label it, x, y went in, and what came out was z, x, y, comma, z. Sorry, z's coming third. X, y, z. And we can do this for every point in the domain. We figure out what the corresponding value that comes out and plot the point x comma y, the two input values, together with their output value. If we collect together all those possible points, then what we get is what's called a surface. And I don't know what the surface looks like in this case. This is just a generic example, but maybe I'll draw such a thing. Maybe it would look something like this. A little bit of perspective lines drawn here as well, just to see what this would kind of look like. So that would be our surface. And this would be the graph of f. What the graph is the set of all triples, x, y, z, so the set of all points in space in R3, such that when you plug x, y into our function, z comes out. So that's what the graph, that's the definition of a graph of a function. It's the same with back in calculus 1. The definition of the graph is the set of all points consisting of the inputs and the outputs. In this case, it's a point in 3 dimensions because there's 2 inputs and 1 output for a total of 3 variables. You might want to think now, if I had a function of 3 variables in, like this one here, f of x, y, z, where would its graph live? Well, there'd be 3 variables in, there'd be 1 variable that comes out. So the graph would consist of points with 4 components. So those would be points that live in 4 dimensions. So the graph would be a collection of points in 4 dimensions. Therefore, the graph would be a 4-dimensional object. Tough to visualize, yeah, very tough to visualize 4-dimensional objects, but we'll see that we can still get a visual for what these kinds of things can look like by looking at projections into lower dimensions, taking slices of them, those kinds of things. So there are ways to visualize these higher dimensional objects in lower dimensions. So that's what a graph is. It's the collection of all points that satisfy the function equation. Z is equal to f of x, y, or the corresponding one for functions of more than 2 variables. Let's look at some examples of functions and their domains. So here's our function, f of x, y is equal to the square root of x squared plus y squared minus 16. Is it possible to evaluate f of 2 comma 1? Well, let's try 2 comma 1. That means I'm going to plug 2 in for x, 1 in for y. So I get 2 squared plus 1 squared minus 16. So that is the square root of 5 minus 16, or the square root of negative 11. And the square root of negative 11, this is not a real number. You might even say, this is not defined. This doesn't exist. We can't square root a negative number. However you want to say it, yeah, you can't plug 2, 1 into the function because you can't find a unique real number that comes out in this case. Having to square root a negative value, it's not a real number. So that means 2, 1 is not in the domain. Now you may say to yourself, hey, I know about complex numbers, and square root of negative 11, yeah, it's not a real number, but it is a complex number. Why don't you worry about that? Well, let's scroll back up. Our definition says that f has to associate with a point in the domain a unique real number. So it has to be a real number that comes out. In other words, in calculus 1, 2, 3, which is this course, and even calculus 4, which is math 252, we are interested in functions where you have real numbers in and real numbers out. So they're functions of real variables with real outputs. And so we won't consider complex numbers. That doesn't mean it's not interesting to consider complex numbers. You would just do that kind of thing in another course, like a course in complex analysis, for example, or complex variables, 322, math 322, or you would do it in one of the engineering courses, math 254, which is vector calculus and complex variables. So you could do it there. But in this course, we're not considering complex numbers. So that would not be in the domain of our function. How about f of 5, 0? Let's see, does that work to plug in? 5 squared plus 0 squared minus 16 is equal to root 9. The square root of 9, that's a positive square root of 9. There's no negative side in front of that. This function here, even defined up here, that's a positive square root in the definition of the function. So this is 3. And yep, perfectly fine. Plug that value in, we get a unique real number out. All's looking good. That's 5, 0 is in the domain, and we know what its output is. How about if I plug 10, 10 in? I get a 10 squared plus a 10 squared minus a 16. So that's the square root of 200 minus 16, or the square root of 184. That's a real number. That's the exact value, but if you wanted to work out a decimal, you could put it in a calculator or a computer and get a decimal expansion of that. It's all fine. I'm just going to leave it in the exact form, which is perfectly acceptable, square root of 184. Now, what about the domain? We found a few values that look like they're fine to be in the domain because we can plug them in and evaluate it. We get a value that 2, 1 that we can't plug in, so it shouldn't be in the domain. What is the domain? Well, the general rule is unless the domain is explicitly stated, then we assume that the domain is as big as possible. The domain is going to consist of all xy pairs that makes sense to plug into this expression. So that's going to be our domain. So what does that mean? Our domain then is going to be the set of all points xy in R2, which makes sense to plug in. What it means to make sense to plug in is that if I plug x and y into the function, I get x squared plus y squared minus 16. That quantity had better be bigger than or equal to 0 in order to take the square root of it. And as long as it's bigger than or equal to 0, I can square root it and get a real number out. So that would be fine. X and y is perfectly welcome to be in the domain. So we need that to be bigger than or equal to 0, or in other words, we need x, y to be in R2 such that x squared plus y squared is bigger than or equal to 16. So this means that the domain, if I'm going to sketch it here, the domain lives in the xy plane, and it consists of all points xy, where x squared plus y squared is bigger than or equal to 16. In other words, it consists of all points that live on the circle of radius 4. It's a circle of radius 4, and everything outside of that circle as well. So I'll shade that outer area in as well. So it consists of all these points, everything outside and on a circle of radius 4. So there's a sketch of our domain. And that point 2, 1, that's inside the circle. That's inside the circle of radius 4. And so it's in the area I haven't shaded because that's an area that's not in the domain. Let's have a look at the next example. G of x, y, z, so a function of 3 variables, is the square root of x over the square root of y plus z. This asks for the domain right off the bat. So what is our domain? It consists of the set of all triples x, y, z in R3, such that it makes sense to plug those values in. To plug into the numerator, I need the square root of x. Well, if x is being square rooted, I need x to be positive. But x could also be 0, and I could still square root that. So it just better be non-negative. That means x better be bigger than or equal to 0. And I also need, so maybe instead of writing the ampersand sign, I'll just put a comma. And I also need that x plus not x plus, the denominator there, y plus z. Y plus z, I should be able to square root that. So that has to be bigger than or equal to 0. But it's also in the denominator. So I can't divide by 0, which means y plus z should not be 0. So I've got a strict greater than symbol there. So notice the subtlety. X has to be bigger than or equal to 0. It's allowed to be 0 because it's in the numerator. But y plus z has to be strictly greater than 0. It's got to be strictly greater than 0 in order to both allow the square root to be evaluated, but also so that I'm not dividing by 0. So there's our domain. Can we work out what g of 16, 50, 50 is? Sure, we just have to plug it in. Maybe as a first quick check, is it in the domain? We check our domain condition. X is bigger than 0. Yep. Y plus z, that's strictly bigger than 0. Yep. That's 100, strictly bigger than 0. So it is in the domain. Probably didn't need to check that because we would have found that out soon enough when we plugged it in, but that's just an illustration of what that domain condition says above. So square root of 16 is 4, square root of 50 plus 50 is 10. So we get a value of 2/5. So g at 16, 50, 50 has a value of 2/5. Now we'll go ahead and sketch some graphs. So we've just worked out a little bit about domains, how to evaluate functions at points. Graphs are going to consist of the set of all points, in this case a function of 2 variables. It's the set of all points in 3 dimensions whose z coordinate is equal to f of the x and y coordinates. So that means I'm going to write down this equation here and say, I'm interested to graph this. I'm interested in all the points x, y, z, such that z is equal to x plus y plus 2. Or in other words, I need x plus y minus z is equal to -2. So just rearranging it a little bit. And I want to find the set of all points that satisfy this. The idea is this is a plane. And we know what that object is, how to graph it. To graph a plane, we just need to either know a point on it in a normal vector, that will tell us how it looks in space, or find 3 points on it, and that's enough to sort of situate it in space and tell us what the plane looks like. So over here, that's what we'll do. The graph is going to be a plane. And we'll go ahead and sketch that. And the way I'm going to sketch it, I'm going to sketch it like this. I'm going to have x going off to the right, y going into the page, and I'll have z going up. You might say, why did I choose to orient my axes, rotate them 90 degrees from how I normally look and have the x going to the right and y going into the page? We'll see that in a second. So this plane, so we're trying to sketch the set of all points x, y, z that satisfy the equation z is equal to f of x, y, or we've just boiled it down now to satisfies this equation x plus y minus z equals -2. Since it's a plane, we know that we can visualize it by getting some points on it. In fact, we only really need 3 points on the plane, and that's enough to be able to visualize it. So let's find 3 points on the plane. What we do is we just look at the equation of the plane and say, I want to find three triples for x, y, and z that satisfy that equation. Well, one straightforward way is to just figure out where does it intersect the axes. Where does it intersect the x-axis? That would be when y is 0 and z is 0. So when y is 0 and z is 0, x has to be -2. So there's 1 point on the plane. What's another point? Maybe I'll see, where does it intersect the y-axis? The y-axis is when x is 0 and z is 0. So I plug those into the equation and I get y is equal to -2. Okay, so there's another point. And the last point I'm going to work out is where it hits the z-axis. So I'm going to take x to be 0, y to be 0, and therefore z is equal to 2, because we have -z equals -2, or z is equal to 2. So that gives us 3 points. Let's sketch them out here. Our 3 points are going to be this point here, which is -2, 0, 0. We've got this point out here, 0, -2, 0. Now you can see why I chose the axes in the way I did. the negative, the values where it hits the x-axis and the y-axis are on their negative sides. So I tried to pull those, the negative parts of the x and y-axis out into the front of the page. So that action was happening out front. And then the last point is 0, 0, 2. So it's that point there. So there's 3 points, and we just need the plane that passes through those 3 points. If I connect them up with line segments, then what I can form is a triangle, and I'll just add some lines to that triangle. I know my plane has to contain this triangle in it. So I'm interested in a plane situated in space that passes through these 3 points, or in other words, it's this triangle, but then just expanding it out in all directions. And that's going to be our plane. So I'll sketch a little bit more of the plane in here, but I'm not going to sketch the whole thing because it's infinite big. But here's our plane. It would look something like this. Maybe I'll angle it a little bit for perspective, and then I'll draw these horizontal lines in. So there's our plane. It's probably much easier to visualize by just looking at the triangle and imagining it extending out. Another way you could get a visual for the plane is to figure out what the normal vector is. And the normal vector in this case, we just read off the coefficients. It's 1, 1, -1. So knowing the normal vector, knowing any of those 3 points we have down below, knowing a point and a normal vector gives us enough information to figure out what the plane looks like. So however we want to do it, the bottom line is that the graph is a plane. So let's have a look at the next example. F of xy is the square root of 36 minus 4x squared minus 9y squared. We'd like to figure out what this looks like. What is the graph of this? So we're going to do the same thing we did before. We want to find the set of all points x, y, z such that z is equal to the square root of 36 minus 4x squared minus 9y squared. And square both sides. Get rid of those square roots. It might help us and try to figure out what kind of object this is. Then we can move everything to one side of the equation. 4x squared plus 9y squared plus z squared is equal to 36. And then I'll divide by 36 just to clean things up a little bit. You may say it doesn't look like you're cleaning it up. You might be making it a little bit messier. Well, perhaps, but the reason I'm doing this is because now at this stage, I can say, well, maybe I know what this looks like. There's a couple of ways to sort of figure out what this potentially could look like. One is to just say, let's temporarily ignore the 9, 4, and the 36 on the bottom. Then this looks like x squared plus y squared plus z squared equals 1. Oh, so it probably resembles a sphere. It's kind of sphere-like, except there's this 9, 4, and 36 in the denominators. But maybe those are stretching or scaling factors, and in fact they are. The next way to sort of think about maybe what this looks like is to get rid of one of the variables. Just say, where does it intersect the xy plane? So take z to be 0. Then if I ignore that term with the z in it, I get x squared over 9 plus y squared over 4 equals 1. And that's an ellipse. It's got some stretching in the x direction, some stretching in the y direction. So there's something sort of spherical in nature going on here with some stretching because I see an ellipse in there somewhere. So maybe this looks like a sphere with some stretching happening to it. And in fact, it is. It's what we call an ellipsoid. This is the kind of thing we'll cover in section 12.6 on quadric surfaces. We haven't covered that section yet, so I'm not assuming we know the things from that section. But there we will study equations like this, and we'll immediately look at this and go, okay, after doing that, we did look at this and say, oh, that's an ellipsoid, and I know exactly what it looks like. But I'm pretending we don't know that information yet. So let's just figure out how do we draw this. So I'll draw my coordinate axes in here. I'll run with the idea that it's kind of a sphere-like, except 9, 4, and 36 might be doing some weird stuff to it, stretching it or scaling it in some way. So I'll figure out how to deal with those. So it kind of looks like a sphere. with some stretching happening. Okay, so now what I want to do is I'm going to find some points on it. So some points on the graph. So we need to find some points. Well, we could do what we did before, figure out where it intersects the axes. So I could take, for example, y to be 0 and z to be 0. That's going to tell me where it hits the x-axis. If I do that in the equation, I get x squared over 9 is equal to 1. Or in other words, x is equal to plus or minus 3. Okay, so that helps because it tells me that it passes through this point and it passes through this point, where this is 3, 0, 0, and this is negative 3, 0, 0. What are some other points on it? Well, where does it hit the y-axis? To hit the y-axis, I need x to be 0 and z to be 0. And that gives me y squared over 4 is equal to 1, or y is equal to plus or minus 2. So it's going to pass through that point, and it's going to pass through that point. So that's 0, 2, 0, and 0, negative 2, 0. And we can figure out where does it hit the z-axis. That's where x is 0 and y is 0. And that's where z squared over 36 is 1. And that means that z is equal to, and if you said plus or minus 6, we're neglecting one small little fact. So it's really just 6 here. And I'll write in not minus 6. You might say, well, why? What's the difference with all the other stuff? The reason is we have to go back to the original function. This is the thing we're trying to sketch the graph of. And the output, when we take any xy value, plug it in, as long as it's in the domain, the output is going to be positive because it's the positive square root of that expression going in. So from this, we have that z has to be bigger than or equal to 0. So that's why I'm excluding negative 6. I can't use negative 6. My z values have to be positive. And so we're just up here at 0, 0, 6. So there's another point on it. And as I said, it's sphere-like. Z values all have to be positive. When we look at it and how it hits the xy plane, we get this shape here. It's our elliptical shape. And then we have that this point, these points are all connected. Again, I'm just kind of drawing a sphere-like shape, but connecting all the points that I've plotted. And so what we get is what looks like a upper hemisphere, but it's been stretched. Stretched in the y direction by a factor of 2, it got stretched in the x direction by a factor of 3, and it got stretched in the z direction by a factor of 6. So this is an upper half of an ellipsoid. So that's what we'll call this thing. An ellipsoid is just a sphere that's had this stretching happening in different directions. So it kind of looks like a football, half a football sort of standing on end. All right, so there's our sketch of that graph. So having some graphs and what they look like in mind is very helpful because there's certain ones that are going to come up time and time again. And in 12.6 quadric surfaces, we'll get some of those basic ones behind us, but we'll come to that section in a little bit. We'll come back to it. Okay, how do we visualize functions of several variables? Well, we could use graphs like we've just been doing, but sometimes those are complicated to get a hold of. Sometimes even sketching them in a graphing utility, maybe I'll just pop over to a graphing utility right now, and we'll get a sketch. We'll get a sketch of that last one. So that last one was the square root, so SQRT of, and I'll have to scroll back in my notes to see what it was, 36 minus 4 times x squared minus 9 times y squared. And We've plotted it here. You see there's some jaggedness happening there. Okay, I'm going to stretch. We know that it got stretched in the x direction by a factor of 3, so I should go from -3 out to 3. And we kind of got this, elliptical shape. Am I missing anything else? You might say, well, it doesn't look like it's going, we had a factor of 6 scaling in the vertical direction. It doesn't look like it's scaled by a factor of 6 in the vertical direction. It looks like it's wider than it is tall. But if we look closely at the numbers, 1 unit in the x direction doesn't look the same as 1 unit in the y direction. The y direction looks, or the y direction, the up or the z direction looks like it's been compressed a little bit. So if I go to axes and scale, oh yeah, the scale on the z-axis is a half the scale on the other ones. So I'll get rid of that, make them uniform scaling, and now it looks like, okay, it's been scaled by 6 in one direction, by 2 in another direction, and by 3 in another direction. But you might be thinking, oh, I still don't like that, that jaggedness going on here. Why is it doing that? Well, what the graphing utility does is it tries to plot a bunch of points and then connect them up in a smooth way and get a reasonable approximation of what the graph should be. And here it's having a tough time when we're around the boundary. It's having a tough time when the x and y values are out at their extreme, sort of on this elliptical portion, because those are going to make this thing under the square root really small. And so it's not getting enough of those points to sort of plot them and get a full picture. So this is just something to be aware of with graphing utilities. Sometimes they give you a good picture, sometimes it's an incomplete picture and it's got some artifacts in it. Okay. So what we'll do now is we will say, well, we know how to sketch some of these things, either by hand or with graphing utilities. But we can look at how to get other information about them by looking at what are called level curves or contours. And so this is basically, the idea is you've got this surface in space and you want to just identify what are those curves that run around the surface that are all the same height, that consists of points that are all the same height, all the same z value. And that's known as a contour. So I'll draw a picture of that. So we've got our generic surface here. Looks something like this. I'm going to draw a little bit of perspective in it. And it looks like that. And like that. So there's our generic surface. We'll draw our coordinate axes in. So there's x, there's y, there's z. And what a contour is just pick a height, whatever height you want, and slice the object at that height. And where the slice happens, it'll produce curves, and those curves are called the contours. So if I pick a height, say somewhere around there, this one might be fairly interesting. I take a plane, so when I slice it, I really am just thinking of I'm taking a plane of that height, and I'm letting that plane cut across my surface. And when that plane cuts across the surface, it cuts it into some curves here. So those are how that plane's going to cut it. It's going to cut it into these kind of two circular kind of type curves. These two curves, however many get produced when you cut it, there may be more, maybe 2, 4, maybe there's a bunch of curves that come up, or maybe there's only one, or maybe there's none, maybe there's no curves. These are called the contour curves. And they, in particular, they're contour curves at height k. So these are the contour curves at height k. We can pick a different height, and maybe we get different shaped contour curves. So if I take another height, let's call it k1, and I slice it there, then maybe my contour curve looks like this. It's sort of one big kind of circular shaped curve. And this is my contour curve at height K1. So those are what contours are. They're just curves on the surface that consist of points all of the same height. What we can do with these is, now since these are sort of curves in a plane, I can just collapse them all down to the XY plane below. And if I do that, so I get that one sort of big green contour curve that looks like that. And I also get these smaller pink contour curves that look like that. These are supposed to be right underneath them. I sort of didn't do a good job of getting them right underneath. So something like this, and then that big green one that sort of goes around them. So collapse them down onto the plane. When I do this collapsing, push them all down onto the plane, we call these the level curves. So the contour curves are the ones that are at the appropriate height in space. When we push them all down to the plane, they're called level curves. And we lose information when we push them down onto the plane. Like, I don't know where that green one came from. What height did it correspond to? How about those pink ones? What height did they correspond to? So we would label these. I would label these the K level curve, and I would label these ones the K1 level curves. And if you've ever looked at a topographical map, so this would be, you're going hiking, you've got a map of a region that you're going to hike through. It's a mountainous region, and you look at that map, instead of, if you go onto Google Earth, you'll see the terrain. But if you take a top-down view on a paper map, you'll see what are typically contour curves. And they'll have elevations like this whole curve as you go around the mountain. This is, this is at 500 feet. This is at 1,000 feet, and so on. And usually above sea level. So those are telling you the elevations. Those are exactly what level curves are. They are curves all drawn in the plane where they're labeled with the appropriate height that they came from as a contour curve. And that helps us, for example, like topographical maps, that's a two-dimensional way to view a three-dimensional object. And we will use these kinds of ideas to analyze and understand functions of multiple variables. So let's do an example of this. Sketch some typical level curves for these functions. So we've got f of xy is equal to x squared plus y squared. We want to draw the level curves for this. So level curves, we're going to say we're interested in curves of the form where the function value is equal to k, where k is some fixed constant. And then we'll let that constant change. So what's the level curve corresponding to height 1? What's the level curve corresponding to height 10? How about height 15? How about height 27? So that will let the k value change to give us different heights. These level curves, these are circles. And we recognize this as the equation of a circle. Circles, and the radius is root k. So now I can go ahead and sketch those. The idea is this function f of xy, it represents a surface in 3 dimensions, but we're going to try to get a visual for it by sketching its level curves in the plane. So I'll say, what does this surface look like? What are all the points that have height 0 on it when z is 0? So that means the level curve corresponding to k equals 0. When k equals 0, the level curve is a circle of radius 0. So it's a dot right at the origin. So that's our k equals 0 level curve. And we can say, well, what's our level curve at when k equals 1? So all the points on the surface at height 1, what do they look like? Well, that would be the circle of radius root 1, or a circle of radius 1. So it would look like this. So that's our circle of radius 1. Maybe I'll label it 1 there. And that's k is equal to 1. And we can say, okay, what's next? Well, I can do one of two ways. I could start naming more k values, different heights, k equals 2, k equals 3, k equals 4. Or I could say, maybe because the radius is going to be root of that value, I'll just pick the perfect squares as my heights. So what about when k is equal to 4? When k equals 4, I get a circle of radius root 4, or a circle of radius 2. So there's my k equals 4 level curve, and it is a circle of radius 2. And then we could do our k equals, so we're running out of colors, maybe one more color here. Our k equals 9 level curve. So these are all the points on our surface that have height 9. And that's going to be our k equals 9 level curve. And so that consists of points that form a circle of radius 3. So now I can start to feel for what this shape looks like. It's going to have a point at the origin, and then it's got a circle that's partway up. At height 1, there's a circle of radius 1. At height 4, there's a circle of radius 2. At height 9, there's a circle of radius 3. And so it looks like all these circles stacked on top of each other. So it kind of looks like this bowl opening upwards. I'll get a little sketch of that. So from this, I can start to visualize, hey, maybe the graph of this looks like something like this, where each height, I get this circle that's sort of getting higher and higher and higher, but it's getting bigger in radius. And why did I draw it with these sort of curved sides on it? Well, the reason I did those sort of curved sides, rather than sort of making it a cone shape, is because if I think about maybe this, I'll draw in a couple of these references here. Maybe I'll draw the whole thing like in green. So those level curves are in gray. Maybe how does it intersect the YZ plane? Well, if I look at my original function, this is really z is equal to x squared plus y squared. And I think, how does it intersect the YZ plane? That's when x is 0. That means this thing's got to intersect the YZ plane in the form of z equals y squared. So this is like a parabola, z equals y squared. So I know it sort of has this curvy shape to it, this sort of parabolic shape. And that's why I said, okay, it's got all these circles stacked on top of each other. They're getting bigger and bigger in radius as I go up. And not only that, they're sort of growing in radius, kind of like in this quadratic shape. So I can use those level curves to get ideas about what the shape of the object looks like. Let's look at the next one. G of x, z. There was really no reason for me to switch from y to z. Actually, why don't I just switch back to y? It's not really going to make any difference. Part of it is that when I'm looking at level curves, I can really, I've got 2 input variables, and I'm just saying the output is the k. So I'm going to, switch back to y here, just so I can work with my same labels. And I'll make that a y and make that a y. And that way I can use x and y as my input label axes as well. So I'm not making things too different than the previous example we just did. Okay, so what are our level curves? We've got level curves are going to be of the form k is equal to the square root of x squared plus y squared. And that means that x squared plus y squared is equal to k squared. So these are circles, and their radius is, in this case, the radius is just k. It's not root k anymore, it's just k because of that k squared in the equation. Okay, so how does that change things? Well, let's go ahead and look. X, y. Again, our k equals 0 level curve. Still a circle of radius 0. Our k equals 1 level curve. Looks like this. It's a circle of radius 1. So we'll label it k equals 1. Our k equals 2 level curve. That's a circle of radius 2. So you might be thinking, oh, well, it looks like you're getting the same level curves. That's k equals 2. Well, sort of. I'm sort of getting the same level curves. I'll draw the last one in and then we'll do a bit of an analysis of this. If I do the last level curve, the k equals 3 one. That's k equals 3. It's a circle of radius 3. The only difference is, it doesn't look too much like a circle. There we go. The only difference is we notice the k values. So I have in that the second one, that k equals 3 level curve. That comes from height 3. It's a circle of radius 3. It comes from height 3. So we've got a circle of radius 3. On the surface, it's up at height 3, whereas that one on the one on the left, that circle of radius 3 actually came from height 9. So this one on the right seems to be, sort of a much lower sort of shape. It's got, at height 3, we got that circle of radius 3, where it wasn't until height 9 on the other one we got that circle of radius 3. So the one on the left seems like narrow and sort of tall, whereas this one on the right, the circles are getting much bigger, faster. You don't have to go up as high to get a wider circle. So that's the kind of information we can gather about our function, and maybe we'll try to get a sketch for what it looks like. So again, it's made up of circles all lying on top of one another. So I'll draw a few of them in here, kind of like a circle and another circle and then another circle. And the question is, how are they stacked on top of each other? Well, I'm going to argue that they're actually straight lines now. They're not this sort of curvy shape like these parabolas we had in the other one. They're straight lines. And why is that? Well, we can think about what happens when I take this expression, z is equal to the square root of x squared plus y squared, and I say, what's happening when it intersects the y, z plane? Well, that means I take x to be 0. So when I take x to be 0, I get z is equal to square root of y squared. So z is equal to plus or minus y. So we get a line like z equals y equals z, and then we get another line like y or z equals negative y. So we get those two lines as sort of the sides. So this is what's known as a cone, whereas the other one sort of got this curvy shape. It's known as a paraboloid. So we're able to detect these things, not only in the level curves, they're circles stacked on top of one another, sort of make up the surface, but how they're stacked on top of each other, how fast the circle grows, the higher up you go. We're able to detect that difference as well. So that's a little bit of information about level curves and how they help us decide what the shape of the graph is. So this is a good one to remember, that the one on the left, f of xy, is x squared plus y squared. It's what we get, a shape like this is what we call a paraboloid. It's kind of like the analog of a parabola, but in 3 dimensions. We're going to use that one very soon. So now this brings us to functions of 3 variables and how to visualize those. As we said, we got 3 inputs, 1 output. The way to visualize it would be in 4 dimensions. It's not going to happen. Can visualize in 4 dimensions. Well, very few of us can visualize in 4 dimensions, let's say. It's not something the general public can do. So what we do is we try to visualize them in 3 dimensions by taking slices or contour curves. In this case, they won't be curves, they'll be contour surfaces or level surfaces. So what we want to do is we want to draw the level surfaces of the function f of x, y, z. That is, we want to draw the surfaces of this form. Now that equation there has 3 variables in it, x, y, z. So that's the equation of a surface in 3 dimensions. That's the level surface. It's like a slice of the 4-dimensional object. And we want to do that for this particular function. So what are our level surfaces going to look like? level surfaces. We're going to say K is equal to f of x, u, z. Oh, sorry, that should be a y, x, y, z. Little typo there. Let's fill that in. That should be an f of x, y, z. What's our level surface? Well, it's something of this form. K is equal to x squared plus y squared minus z. I'll just rearrange this a little bit. Z is equal to x squared plus y squared minus k. So that's what we're wanting to sketch. If I scroll back up, I already know how to sketch now from above. I know how to sketch a z equals x squared plus y squared. It's this paraboloid, this sort of bowl opening upward kind of shape. What I want to sketch down here is just the equivalent thing for different values of k. And all that k is doing, since I'm subtracting it, all it does is just dropping it. If k is a positive number, then I'm taking x squared plus y squared, minusing a value. So I'm dropping the graph a little bit. So what it means is I've got level surfaces that look like this: x, y, z. If I draw the level surface for k equals 0, then I'm getting a shape that looks like this. This is the exact shape we had above, which we sketched on that diagram on the left. So that's, we would label this. That's our k equals 0 level surface. What about k equals 1? Well, when k equals 1, we get x squared plus y squared minus 1. So it's this whole picture, but it's shifted down. So it's shifted down 1 unit. So it looks like this. Of course, it keeps opening up forever, but I'm only going to draw a truncated version of it. So like that. It's like this another bowl of the same shape, but just pulled down a little bit. And that would be k equals 1. We could do a k equals minus 1. That would be shifted up 1 unit. We could do a k equals 2. I'm just picking arbitrary k values, 0, 1. Let's do a k equals 2 value. I'll do that one in pink. So we're down here, k equals 2. Actually, I shouldn't use pink to continue the axes on, but I'll use pink for the object. So now we're down here at k equals 2. Again, we get that same sort of parabolic shape. And that's our k equals 2 level curve, so our level surface. So there's our level surfaces. You may say that looks complicated. Well, the way we view these is as follows. We have this function right here, and I'm trying to make sense of what this function, how it's behaving. Let's just pretend, for sake of argument, that it's a temperature function. So this says that the temperature at the point x, y, z in space is given by x squared plus y squared minus z. So that's the temperature in space. What are these pictures I've just drawn? Well, that green surface is the set of all points that have temperature 0, because they all correspond to the z value 0, the output of the function being 0. So everything on that green surface has temperature 0. Everything on the orange surface has temperature 1. So those are all the values in the input, all the values in the domain, and you plug them into the function, give an output of 1. That's what these level surfaces are. They're all the values in the domain, which when you plug them into the function, give the same value out. And similarly for k equals 2, all those things on the pink surface are the values that when you plug them into the function, give a temperature of 2 out. So then we can say, okay, suppose you're in a location in space where the temperature is 0. Which direction do you need to go to get to temperature 1? Which direction do you need to go in order to get the temperature increase? And we can see even those kinds of things from this picture. I need to go from the green surface to the orange surface. So I need to move out of the green surface, sort of, out of it. If I'm thinking of it as a bowl, I need to move off of the bowl. Whereas if I wanted to drop my temperature, I move inside the bowl that I'm currently on. So these kinds of bits of information we can see from these kinds of pictures. And we will explore these things throughout chapter 14. We'll get to that in in later sections about which direction do I need to move in. It's going to be related to tangent planes and normal vectors, and all of that kind of good stuff will come up here. But this is just getting a feel for what level surfaces and level curves are. All right, let's have a look at the final example. Verify that the contours of the surface z equals sine of the square root of x squared plus y squared are circles, and then use this to convince yourself of the graph as shown. Okay, so I want to verify that the contours of this surface are circles. How do we do that? Well, the contours, or in other words, the level curves that we're interested in, are going to be of the form k is equal to sine of square root of x squared plus y squared. So I'm interested in all those xy values for which sine of the square root of x squared plus y squared equals a constant k. I'm just going to take a step back from this for just a moment and think, what kind of answer do we expect? I'm trying to find conditions on x and y so that sine of them is equal to k. Okay, that sine may be causing a bit of an issue, so maybe I'll look at a picture first. I'm just going to ignore the sine of x squared plus y squared and just think, I've got a sine function. Sine function looks like this. And I'm interested in knowing all the possible arguments, all the possible values I can plug into the sine function for which the output is k. So I'm really thinking of the output being k. Now there's our line of height k. What were the inputs? Well, the inputs would be something there, another value there, another value there, another value there. There'd be infinitely many values that go in that would give me that output. And then I can look at this a little bit more closely and say, if I knew this value, maybe I'll call this value theta, then I can get a lot of the other values, because this would be theta plus 2 pi, this would be theta plus 4 pi, this would be theta minus 2 pi, and so on. But that still leaves me trying to figure out what that value is. So I'd also need to find another angle. If I could find that angle theta, then, the alpha, then this one would be alpha plus 2 pi, and so on. So I need at least to figure out 2 of the angles that when I plug them into sine gives me k out. Okay, so that at least I'm starting to figure out, what is it I need to find? I need to find a couple of values that when I plug them into sine give me k out. Okay, now let's look at another view of what the sine function is. This is our unit circle view. And with our unit circle view, the idea is that given an angle, theta, the y value of this point, well, the x value is cos of theta, the y value is sine of theta. That's the definition of sine and cosine as functions. They give the x and y coordinates on the unit circle. So it's the unit circle. And again, if I think about it this way, I want to know what are the angles that give me a sine value of k. So the y value I want to be k. So that's going to be a line at height k. And again, there's going to be one angle that I can get, but there'll also be another angle that I get. Maybe I'll color this one in a different color, alpha. And so can I figure out either of those angles first? And the first statement is absolutely. We have that if sine of theta is k, then theta is arc sine of k. And arc sine of k is going to give us that angle between negative pi by 2 and pi by 2. So in quadrants 4 or 1, that give us that k value. If I'm thinking k is positive in this case, then arc sine is going to give us that angle between 0 and pi by 2. So I can get that angle theta using arc sine. How do I get alpha? I just noticed that this is also theta. So that alpha would be pi minus theta, or pi minus arc sine of k. All right, so now I've got all the ingredients. So this was all review about trigonometry and working with inverse trig functions. This was a high school review, but that's the ingredients we need, because now I can come back here and say, okay, so what are my contours? Well, I'm looking for solving this expression for isolating the x and the y's. So what I get is that the square root of x squared plus y squared is going to be arc sine of k plus 2n pi for any integers. So that's these values here. That's this value. Maybe I'll make it in pink. That's this value and this value and this value. So those are all the values that give us that k out. But then I had to get the other ones. So I also have, or the square root of x squared plus y squared is equal to, and then it's that alpha plus 2n pi, and alpha is pi minus arc sine of k plus 2n pi. And so there are the two curves. Well, that's not precisely two curves. There's infinitely many, but there's two families of them. For each n, we get a curve. So for given height k, how many curves are there? We can kind of see that from the picture that this thing is waving. So there's going to be, down, there's going to be a curve. Let's say there's a curve here at a particular height. There's another one on the next band. It might be hard to see those. There's a curve there on that one. There's a curve on the next band. Then there's a curve on the next band out here, and so on. We have these nested circles that are all forming our level curves. But there's actually, wherever I've drawn one of them, there's also another one. So you can sort of see it. There's one right next to this one, really close to it. It's sort of the one on one side of the hill, and then you go up the hill and over, and then you've got the one on the next side of the hill. So they sort of come in pairs. We've got the one inside and the one outside because they're sort of a hill. The idea is we've got this one here and this one here, and they live on opposite sides of the hill. This one and this one, opposite sides of the hill, and so on. So we're getting these circles that are living on opposite sides of the hill from each other. So there's our circles. Why are they circles? They're circles because we have x squared plus y squared is equal to, and I can square this, arc sine of k plus 2n pi squared, and x squared plus y squared is equal to pi minus arc sine of k plus 2n pi, and that's all squared. And so there are these circles that are our level curves. All right, we can go ahead and sketch this. Might as well just do that since we do have this open. So we'll go for an explicit surface. What is our surface? It is sine of the square root of x squared plus y squared, squared. And so that's it. Yep, z is equal to that. And you may say, oh, it doesn't look like the shape that I have. Well, I can bump these things up. Maybe I'll go out to 30 and 30 and 30 and 30. And now we get that rippling effect that we expected. And so there's our corresponding object, and we can see that the level curves are circles. And there's one on the inner portion of one of these mounds, and then another one on the outer portion, and so on all the way down. All right, so that's it for this section. Thanks for watching.